So this week, the only lesson we're going to look at is part 6.3, which is on sine and cosine. So that's what we've started looking at. And we're going to do something we've done many times with the graphs, which is just shift them, stretch them, and reflect them. So everything that we've already learned about shifting, stretching, and reflecting is exactly the same. Nothing changes with sine and cosine. Okay. The only thing I have to show you is what basic sine and cosine look like. And then once you know that, you can shift it or stretch it however you need to. Okay. The first thing is these kind of graphs are what we call periodic. We haven't studied any graphs that are periodic yet. But periodic basically means when you sketch the graph, it's going to repeat itself over and over. Right? So once you know what one section of the graph looks like, the next section of the graph looks exactly the same as the first section. So let me show you an example. So let me take, you don't have to graph this on the calculator, but I'm just going to take the graph of sine and show you what it looks like. Actually, does anyone already know what it looks like? Yeah?
So it's like up and down, like I don't know the word for it, just it's like up and down, keeps repeating, same height, back and
Okay. Yeah. Yep.
It looks like a wave.
Yeah, it looks like a wave. So if let's do, we're going to use zoom 7 a lot. So usually we do zoom 6. That's the standard window. Zoom 7 is what we use a lot for trig. Okay, so let's take that. And if I were to look at what I would call one section of that wave, it would start here, it would go up, it would go down, go back up. It would stop right there. That part that I just did in red, and there's a name for it, but we're just going to call that one section. If you take that and you copy and paste it, left and right, forever, you will get the entire graph. Okay? It's just that one section in red repeated over and over. So the y values for that section in red start at 0, go to 1, 0, -1, and 0. There's other y values in there, but I'm just kind of naming the key ones, the important ones. And you're going to keep seeing those y values repeated. 0, 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, -1, 0. Those y values are going to keep repeating. Now you have to travel a certain distance before they repeat. The distance you have to travel in this one is from here to there. It's, if you want to look at it in terms of like the tick marks, it's traveling 4 tick marks. We have to know how long that distance actually is. So the length of that interval that you have to travel before the graph will repeat, that's called the period of the graph. And for sine and cosine, the period of the graph is 2 pi. It is 2 pi. Now the 2 pi is if you don't stretch it, compress it, do anything like that. That's just the normal period, or you can also call it the cycle length of the function. So this is 2 pi. From there to there. If you don't travel 2 pi units, you will not travel one full cycle. You've got to travel 2 pi units to get one full cycle of the graph. So you'll hear me use the 2 words interchangeably, a period of the graph or one cycle of the graph. Cycle is sometimes used in other disciplines. You might see like, see that abbreviation. What does that stand for? Yep, Hertz. Hertz. And Hertz is cycles per second. It's a measurement of how fast something is cycling in 1 second. And does anybody know where you see Hertz used?
frequency.
Yep, when you talk about frequency, so sound frequencies are measured in hertz. Radio frequencies are also measured in hertz, totally different. Sound frequencies are like a compression wave. Radio frequencies are an electromagnetic wave. Okay, so you can't hear those directly, but with a radio you can pick them up. Another place you might see hertz used is when you're talking about electricity. 60 hertz is what the electricity runs at in the US, 60 hertz, cycles per second. So we're talking about the kind of electricity where you plug something in your house, not your car. Other countries, they don't use 60 hertz, they use 50 hertz. So what that means is if you have a device that's not designed to work on 60 or 50, work on both, then you have to be careful where you plug it in. A lot of devices, if you look at it closely, like transformers, the power bricks, you plug them in. If you look at it, it'll say 50/60, which means it can work in either country as long as it physically fits into the outlet. For that, they make different adapters to make it so it fits in like European outlets and stuff like that. Right? But if it doesn't say 50/60, then you have to be careful about plugging it in. So we'll use cycles a little bit. Period is what we use more though in this class. Okay, the length of one cycle is 2 pi, or the length of one period is 2 pi. Say it either way. So a couple things about the graph. That's the graph of sine. Okay, and that graph is symmetric over the origin. Okay, what that basically means is if you reflected it over the x and then over the y, it would look like the same thing. Okay, so let me take this part in red. Let me flip it left, right. So what I wanted to do is reflect it over the y-axis, and that's how it would look. And now let me reflect that over the x. So let me flip it up to down. Looks exactly the same. Okay? So because you can do that double reflection and it looks the same, that's called symmetric over the origin. Now, if we look at cosine, let me move this up. So this is sine. Okay. Cosine looks similar, but it is a little bit different. I'll graph it at the same time so you can see the difference. What is the difference between sine and cosine? Matt?
Cosine seems to be a bit shifted towards the left.
Yeah, so when we talk about sine and cosine, they really are just shifts of each other, left and right. Now, if you try the same thing with cosine, try to say, well, is it symmetric over the origin? The answer is no. But it is symmetric over the y-axis. So if you take this part right here, and you reflect that horizontally, flip it left, right, and then move it, it lines up exactly with that other section. Okay, so it is symmetric over the y-axis. Okay, so what does that mean as an equation? It means those two things I just wrote down up there. When something is symmetric over the origin, that means if you put the negative on the inside or the outside, you get exactly the same result. Okay? I tried to show it to you as a picture. I can also try to show you it doing a calculation. Let's put our calculator in degrees. Let's do the sine of negative 10. Okay. What should that be the same as? If I didn't want to write it with a negative inside the parentheses. Rush?
Negative sine of positive 10.
Yeah, negative sine of positive 10. Okay, whenever something has the symmetry over the origin, you can take the negative and you can put it inside, or you can put it outside, and you get the same result. How about cosine of negative 10? What should that be the same as based on the formula? Yeah. Cosine of 10. Yeah, and it comes out exactly the same. And that's because when you put a negative on the inside, that's a horizontal reflection. And I just showed you when I took this black section and I reflected it horizontally, it looks exactly the same. So the negative reflecting horizontally doesn't make a difference with a graph of cosine. Okay. Any question on that? Okay. It's useful to plug when we get into values where we don't want to have a negative on the inside. Well, if we have a cosine, we're going to be able to just get rid of the negative. And if we have a sine, well, we can't get rid of it, but you can put it in front. All right, so how do we graph sine and cosine? Well, they are a wave, so we need more than just a couple points. A couple points is good for a line, but I recommend 5 points. And the 5 points that I recommend will give you the beginning, the end, the middle, the high point, and the low point. It'll give you all 5 of those. You can do more, but you don't really need to. Okay? Five is what you need. And because we're going to graph only one cycle, this is what the graph is going to look like. Yes, the wave does continue on forever left and right, but the idea is if you can sketch one section, we know every other section looks the same. Okay, so all we have to do is sketch one cycle of the graph. And the points that we pick, because you're sketching 5 points and you're doing it from 0 to 2 pi, that gives you 4 sections. That's your first section, second, third, fourth. So if you want to break up one cycle into 4 sections, each section represents 90 degrees. So this coordinate is 0, 0. This one would be 90, comma 1, 180, 0, 270, negative 1, and then 360, back at 0. Okay, so they're all spaced 90 degrees apart. That's how you get 5 equal points. So what I want to do now is write those points down that I just said. Okay? Set them for sine, we're going to write them for cosine. And once we have those 2 tables, we're going to know where sine and cosine starts all of the time. Then if we have to shift it, we'll modify the table. Okay, but it's very important we get the original tables correct. Okay, so let's start with the sine table. So what I've done is I've written down all the points that I have graphed right there. 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and 2 pi 0. Okay, those values are just 0, 90, 180, 270, and 360, but in degrees. Okay, and I'm going to put cosine up. I'm going to use the same x values because we want to keep everything equally spaced, 0, 90, 180, 270, 360. But I want to write down my y values. Remember, it's shifted. So the y values for sine and cosine aren't exactly the same. But they're similar. So what I'm doing is setting up the screen to show you exactly one cycle of cosine. That's one cycle. It's the first cycle that you see to the right of the y-axis. So for cosine, when x is 0, what's y? Yeah, right. Y is at 1. How about when we get to pi over 2? That's our first quarter point. Jake?
Y equals 2.
Y equals what?
1.
So we started at 1. Nothing's going to repeat again until we get to the end.
0.
Yep, so pi over 2, we're at 0. Dario, how about when we're at pi?
-1.
-1, that's the lowest we go. And Ethan, how about 3 pi over 2?
0.
Back at 0. And Lens, how about when we get to 2 pi? We go back to 1. Okay, those are the y values for the first cycle of cosine. Now that we have those original tables, we can modify them however we want. We can shift up and down, left and right, stretch up and down, left and right, and reflect. But these are the only points that you have to work with. Okay? You don't have to sketch any more than what's in that table. Any questions on those original tables or where those values come from? So this is something that you guys already know because we've done a lot of transformations. But when you do one transformation at a time, it only affects one value. So if you shift up and down, well, it doesn't do anything to the x's. Shifting up and down would only affect the y's. Okay? If you stretch left and right, then that would affect the x's. It wouldn't affect the y's. So for today, we are only going to do one individual transformation at a time, which means when you're working with these tables, you're only going to have to worry about changing one column and keeping the other one the same. Okay? When we get into multi-step transformations, which will be next time, but we normally do that all in the same day, but just we won't do that for today. But when we get into multi-step, then the x column and the y column could both change. But for today, one column will stay, one column will change. All right, so let's look at the 4 transformations. Okay, the first one is a phase shift. Phase shift is what they call a horizontal shift. We should already kind of know how that works. What kind of arithmetic is involved when you shift something left or right? Yeah.
Addition and subtraction.
Yep, it's either addition or subtraction. And is the addition or subtraction inside the function or outside the function?
Inside.
Yep, inside. It's exactly the same with this. So a phase shift is when the graph is translated left or right. And it's when you add or subtract a value inside parentheses. Which way would add shift the graph? Addition would move it to the left, and subtraction
To the right.
to the right. Yep. So that's still true. So if you have x minus a value, everything is going to move to the right. If you have x plus a value, everything moves to the left. Okay, so I really am breaking it down step by step, probably a little bit more than we need to because we've done a lot of transformations, but we've got time to just really break it down, so that's okay. All right, so what happens to those 5 points in the table? So when I say 5 key points, or to determine the 5 new points, I'm talking about the 5 points in the table. Well, when you shift left or right, which column in that table is not affected? Yeah, the y's. Yeah. So you can copy all the y's down from the original table. Okay, and that is something I'm going to want to see. I'm going to want to see what is the table. Here's the table you started with, I just gave you. Tell me the new table after you shift it left and right. Okay, so you don't have to worry about changing the y's at all. Now, for the x's, we have to remember we do the opposite. So if you see something like x plus pi, plus is going to shift the graph to the left. The only way you can make x values move to the left is if you make them all smaller. So that means you have to subtract from pi, from all of them. If you see something like cosine of x minus pi over 2, a minus is going to shift it to the right. The only way that a graph can move to the right is if all the x values get bigger. So you have to add to make them bigger. So whatever you see inside parentheses, we already know it, but just remember, always do the opposite. Yeah? Yeah, just a second. Okay, so let's try a couple shifts. You'll notice that when you shift, you generally don't shift by just random numbers. Most of the time, sine and cosine are shifted by either pi, pi over 2, pi over 4. Yeah, you can shift by anything, but those are the common ones. So pi is how much of a shift in degrees? Yeah?
180.
180. And then pi over 2 is how much of a shift? Yeah?
90.
90. So this is a quarter cycle shift, because a full cycle is 360. And pi over 2, and pi over 4, that's 45 degrees. So that would be shifting it by 1/8 of a cycle. All right, so we're subtracting inside parentheses, which means it is moving left and right, left or right. Which way is this graph going to move? Yeah,
Right.
it's going to move right. Since it's moving right, which column from the original table stays the same? Yeah,
The Y.
the y's. Can you remind me what the y values are in the original table I gave you? And make sure you look at the sine table.
It's that a pencil?
Can you have a what?
A pencil?
A pencil? Yeah. So yeah,
Would it be 0, 1, 0, -1, 0?
yeah. Okay, so half the table's done. 0, 1, 0, -1, 0. Now, let's write down the original x's. Can you tell me those as well? I'm not going to put them in the table. I'm going to put them off to the side.
Okay, 0, pi over 2, pi, 3 pi over 2, and 2 pi.
2 pi. Now, those are all going to be shifted to the right. So are we going to add or subtract all of them? Yeah, we're going to add. And how much are we going to shift all of them? Yeah,
5 to 2.
pi over 2. That's it. Okay, since we are working in radians, we don't want to deal with decimals. We'll just keep everything as fractions with pi. So we've got final answers are going to be in this box. So we've got pi over 2. Okay, next one is 2 pi over 2, which is pi. If you add pi over 1 and pi over 2, you'd have to make it 2 pi over 2. So 2 pi over 2 plus 1 pi over 2, 3 pi over 2. 3 pi over 2 plus 1 pi over 2 is 4 pi over 2. And again, we'd have to find a common denominator, and you would get 5 pi over 2. If you write everything with a denominator of 2, you'd see a pattern here. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. Okay, it's always a nice pattern. And that's it. That's how you find all the points when you shift horizontal. Any question before we do our sketch? Now, were all these values that I just circled in purple, were they all equally spaced when we started? Jackson, what do you think?
Yes.
Yeah, they were all equally spaced, and we shifted them all the same amount. Are they still equally spaced?
Yes.
Yeah. So when we label our sketch, okay, I don't want to get into using decimals because that's going to be messy. The only condition when you label your axes is use things that are equally spaced. Well, all these values are equally spaced. So we've got 0, pi over 2, and I'm just going to use the x values that I already have in the table. Pi, 3 pi over 2, 2 pi, 5 pi over 2. I wrote them lower than the tick marks because I'm going to be drawing close to the axis. And what's the highest y value that we have? Yeah.
1.
And the lowest?
Negative 1.
-1. Yep. That's how you set up your sketch. Okay, and now plot your points. So pi over 2, you're at 0, 1, 0, -1, back to 0. That's the new sketch. If you wanted to show the original would look something like about like that. Okay, so the one in blue. Oops, let's fix that. So this has been shifted to the right a quarter of a cycle or 90 degrees. Any question on that one? All right, let's try another shift. Is this a bigger or smaller shift than the last one? Yeah.
Bigger.
Bigger, yeah, it's double. We're shifting by pi instead of pi over 2. Again, we know it's horizontal. So which column in our table stays the same? Yeah, y's. And what are my y values for cosine?
1, 0, -1, 0, 1.
Okay. We can put the original x's. Don't put them in the table. Just put them off to the side. And all of those x's need to get shifted. Can anybody tell me what I'm going to do to all of them? Yeah?
Subtract 5.
Subtract pi. Yep. And we'll put all our answers in that table. Okay, so when we subtract pi, we get negative pi. Pi over 2 minus pi, if you find a common denominator, negative pi over 2. Pi minus pi is 0. 3 pi over 2 minus pi. And 2 pi, take away 1 pi, is 1 pi. That's your table. Any question on the table? Okay. Now when we sketch it, we're going to do the same thing we did before. We started with x values that were equally spaced. We finished with x values equally spaced. So I'm going to use those x values in my table. But I need to go to negative pi over 2. I can label the axis as 0, but we know it's 0. Pi over 2 and pi. Okay, and we're starting at 1. So 1, 0, and then 0, negative 1. 0, back to 1. Now it looks kind of like a V shape, but remember, it's that. It should not. It shouldn't have like a sharp point to it anywhere. Try to make it look curved, like this. Any questions on that? Okay. So that's all we're going to be doing. We're just going to try shifting some up, down, left, right, and then some stretches. All right, let's try this one. Okay, this will be our last horizontal shift, then we'll do some vertical. What are my y values for sine? Yep, Marcel.
0, 1, 0, negative 1, 0.
Yep. So we've got our y values. Can somebody give me the original x values for sine? We're just going to put those off to the side. Yep.
0, pi over 2, pi over 2.
Okay. And now what am I going to do to all those x values? Because they're all going to shift. This is our smallest shift yet, but they are going to shift. Yep.
Subtract by pi over 4.
Yep. Subtract pi over 4. Okay, so the first one is negative pi over 4. This would be 2 pi over 4, take away 1 pi over 4. 2 pi, take away 1 pi. Is 1 pi over 4. 4 pi over 4, take away 1 pi over 4. Is 3 pi over 4. What's the next one going to be? Yep.
5 pi over 4.
5 pi over 4. And the last one? Yep.
7 pi over 4.
7 pi over 4. So the denominator is going up by odd numbers. Negative 1, 1, 3, 5, 7. The next one would be 9 pi over 4. But that's a full cycle, so we stop. Okay. Now, let's think about if you were putting these numbers on a number line. Okay, and let's put 0 right there. Just the numbers in front of pi. Negative 1, 1, 3, 5, 7. Negative 1 would go right there. 1 would go right there. Where would 3 go? Oh, Nick?
Can you repeat?
Where would 3 go?
3 pi over 4.
Just 3.
2 after 1.
Right, we have to skip. Okay. It doesn't look like we had to skip at first because 0 was already labeled for us. But the point there is to notice you are skipping. Okay. That would be 5, and that would be 7. So when we set up our labels and we do it with pi over 4, it's going to look exactly like that. Okay. We are skipping every other tick mark because we have to. That's how the numbers are. Okay, so we've got negative pi over 4. We don't have to label that as 0. We can, but we know the axis is 0. This is 1 pi over 4. And then we're skipping 2 pi over 4 and going to 3 pi over 4. Skipping 4 pi over 4, going to 5 pi over 4. And then you're skipping 6 pi and going to 7 pi. Okay, so it's not a huge thing, but it is important to just recognize that is how your axis is set up this time. Okay, and we start at 0 and do our standard y values. 0, 1, 0, Any question on why I had to skip there? If you didn't skip, it would be like putting 3 right here. That's not right. That's 0, 1, that's 2. So you got to skip and go to 3. All right, so that's shifting left and right. That's one of the harder ones because you have to deal with fractions with pi. Shifting up and down, that one's easier. What kind of arithmetic is involved when you shift up and down? Yep.
Addition or subtraction?
It's still addition or subtraction. It's just like shifting left and right. But where is the addition and subtraction now? Yeah.
Outside the function.
Outside. Yep. So vertical shift is going to move the graph up or down. I'm using the letter D because when we write all of them out, the vertical shift is always the last one. And this is when what you add or subtract is outside the argument. It's not backwards. Positive is up, negative is down. Bless you. Okay, so we'll do 2 of these, and then we'll finish up with the stretches. All right, this time when you find your 5 points in the table, because you are moving up and down, the x's do not change. So all the x values for the next couple problems are 0, pi over 2, pi, 3 pi over 2, 2 pi. If the x values are going to stay the same, then the y's are going to change this time. Just add or subtract whatever d is to the original y values. So all you're going to have to do is add or subtract a number from 1, -1, or 0. Very easy arithmetic. Let's try this one. Okay, first step, identify what kind of transformation it is. It's addition. It's on the outside. It means it's going to shift up or down. Okay, so Travis, which column is going to stay the same now?
X.
Yep, and can you give me my x column for cosine?
0, pi over 2, pi,
Yep.
3 pi over 2, 2 pi.
And I'm going to write the column for y that is changing off to the side. Dario, can you give me my y values for cosine?
1,
Mm-hmm.
0, -1, 0, 1.
Perfect. So those are my y values. And now what am I going to do to all those y values? Yep, just add 2. So we get 3, 2, 1, 2, 3. That's it. That's how you shift something up or down. Right, now we'll fill in our table. We did the table. Let's do the sketch. This time, we don't have to change any of the x labels. So 0, pi over 2, pi, 3 pi over 2, 2 pi. I'm also not worried about putting my labels right up near the graph when I sketch, because I know my sketch is going to be out of the way. If I shifted up like 20 units, then I might scale my y-axis to go by 2s or 5s or something. But we're only going up 2 units, so 0 to 3 is all you need. Right. And we have 3, 2, 1, 2, 3. There you go. So that's a cosine function shifted up 2 units. Any questions at all? All right, let's try this one. How about Marin? What's going to happen in this one?
It's going to go down 3.
Yeah, it's going to go down 3. So which column, when you're writing coordinates, is not affected by moving down? The x's. So fill those out. And now the original y values would be, how about, Greg, can you give me my original y values for sine?
For sine.
Mm-hmm.
0, 1, 0, negative 1, 2. I mean, and 0.
0, 1, 0, negative 1, 0. And what are we going to do to all of them?
Plus 3. No, minus 3.
Minus 3, because it's moving down 3. And Vanessa, if I minus 3 from all of them, what does that give me?
Negative 3, negative 2, negative 3, negative 4, negative 3.
Yep, that's it. So that's our sine function shifted down 3. Okay, since it's only down 3, I'm going to keep my y-axis going by ones. I don't think I need to go all the way to negative 5. That's fine. I am going to put my labels above the axis so they're out of the way, though. So 0, pi over 2, pi, 3 pi over 2, 2 pi. All right, so 0, we're at negative 3. Pi over 2, we go up to negative 2. Then pi, we go back down to negative 3. Negative 4. And back to negative 3. Okay, so that's your sine function shifted down 3. Any questions on that? Okay. All right, so we just looked at stretching left and right. I'm sorry, shifting left and right, shifting up and down. Now we'll finish with stretching left and right and stretching up and down. Okay, when we stretch up and down, we're going to be changing the height of the wave. That height has a name, and it's called the amplitude. So sometimes you might see a vertical stretch called an amplitude change because you are changing the height. Okay. Because the amplitude is measuring the distance from the center to the highest point on the wave, or from the center to the lowest, it would be the same. What kind of number do you think amplitude always has to be? Yeah?
Positive.
Positive, yeah, because it is measuring a distance. Yep. When we do an amplitude change, or vertical stretch, as we're used to calling it, that is when you multiply, and you multiply on the outside. So one thing I could do is just give you a question like this. Don't even have to graph it. And I just ask you, what is the amplitude? If the amplitude is all you want to know, it's the absolute value of the stretch. This would have an amplitude of 3. What would be the amplitude of this? Yeah, it'd still be 3. The negative is going to cause something else, which we've talked about, but it still has an amplitude of 3. So just take the absolute value of the stretch amount, and that will always give you the amplitude. Okay, so amplitude change is going to stretch or compress the graph vertically. The name we're used to using is vertical stretch. What would be the amplitude of 3 cosine x? Yeah, 3. What would be the amplitude of 4/3 sine x plus pi over 2 plus 6? Yeah, 4/3. Yeah. There's a couple other transformations that we talked about. There's movement up and down and left and right, but that doesn't affect the amplitude. Okay, because remember, the amplitude isn't how high that it goes. Right? If I took a graph like this, that still has an amplitude of 1. It has a maximum value of 16, not 15, 16. But the amplitude measures the distance from the center of the graph to its highest point. And that would still have an amplitude of 1. How about that one? Y equals -2 sine x. Yeah, just 2. Yep. All right, so making the table. Which column is not affected by stretching up and down or compressing up and down? Yep. X's. Yep. So that makes the arithmetic for this transformation very easy. The x's are going to stay the same. And the y's, well, to find the new y's, you're going to multiply the old y's by the stretch. Don't take the absolute value of the stretch. Just take whatever the stretch is. Because if it's a negative, that's going to cause it to flip as well. All right, so let's try 3 cosine x. X's stay the same. So Ethan, what are my original x's for cosine?
0.
Yep.
Pi over 2. Pi. 3 pi over 2.
2 pi. Now we need to find the new y values, but to find the new ones, we need the old ones. Okay. How about Jaden? What are my original y values for cosine?
1,
Yep.
0, -1 plus 0.
And what are we going to do to all those y values?
Multiply by 3.
Yep. Times them all by 3. That's it. So 3, 0, -3, 0, and 3. Now, a lot of my graphs are going to look the same when I do stretches because I change my axes. I'm just going to make this 3 and -3. So it's not even going to look like I stretched it because I changed my scale. Right? But that, to me, it's easier to change my scale than to have to draw something bigger and bigger. So 3, 0, -3, 0, 3. And I should put my labels on here. The only time you don't have to label is if you're going by ones. Okay, whenever you go by ones, it's understood that if you don't have labels, that's what it means. But technically, I am not going by ones. I'm going by pi over 2s. Okay, so we got everything. Just draw your sketch. Okay, any question on that one? What's different? This is still a multiply on the outside, but why is this transformation a little different than the last one? Yeah.
The y values we kind of have.
Yeah, this time it's actually going to be a compression, not a stretch. But because I'm going to scale my axes, you're not really even going to be able to tell from my picture. 0, pi over 2, pi, 3 pi over 2, 2 pi. And can you tell me what half of my y values would be?
0.
Yep.
1/2. 0. -1/2 and 0.
Perfect. That's it. So I would make this a half, -1/2, and then you could just do your sketch. Any question on the table for that one? The table is what's worth most of the points in this kind of problem. I would make the table 10 points. You get 1 point for each x and y value you get right. And then the sketch, I would probably make that worth like 2 points. So the table's a lot more. Right, and let's try this one. What's really happening in this one? With the negative in front of the cosine x. Yep.
It's getting multiplied by -1.
It's getting multiplied by -1, so is that going to change the amplitude? No, there is no change in the amplitude, but something's going to happen. So what is going to happen? Yeah.
It's going to reflect over the y-axis, or the x-axis.
X-axis. That's a vertical reflection. So yeah, it's going to reflect over the x-axis. So all these stay the same. Those are your original y's, but they're all going to get multiplied by -1. So all the y's just switched. So that means we're going to start here, 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 there, and there. So normally cosine has that U shape. Now this is flipped over because it's been reflected. Okay. Any question on it? All right, so last transformation. The last transformation is when we stretch or compress horizontally, and they call that a period change. What's been the period of every graph we've done so far? If you measure the distance from the start point to the stop point. They've all had a length of how much?
2 pi.
They've all been 2 pi. Every single one of them. When you stretch or compress horizontally, that 2 pi can change. Okay, it's not going to be 2 pi anymore. So stretching and compressing horizontally, we know that that's multiplication. The difference is it's inside instead of outside. We're only going to be looking at examples where the b is greater than 0. If it was less than 0, we could have a horizontal reflection. But we're just going to be looking when b is greater than 0. What happens if the b value is really big? Let's say b was 5. What's going to happen there? Yeah?
It's going to be really compressed.
How much if b was 5?
Like a fifth.
A fifth, yeah. So the bigger that you make b, the more compressed it's going to get. B is 5, the graph is going to become 1/5. If b is 3, it's going to be 1/3. So then what happens when we try a number smaller than 1? What does that do to the graph? Vanessa?
It's gonna stretch it.
It's going to stretch it, yeah. So what if b was like 1/4?
It's gonna be by 4.
By 4, yeah. It stretches it 4 times as much. That's no different than anything we've said before. It's the same thing. All right. So then let's say the period was 2 pi. And we had let's say the b value of, let's say we had a b value of 1/2. What would be your new period? If the original period is 2 pi, and you do a b value of 1/2.
It would just be 5.
So 1/2, what does that do to the graph?
It stretches it.
Stretches it, which means this number gets even bigger.
So 4 pounds.
4 pi, yeah. So again, original period's always 2 pi. Let's say we had a value of, I don't know, let's just do 2. What would be your new period if the value of b was 2? Yep, pi. So does anybody see what you can do with this value and this value to get that value? Yep.
You multiply the original AP to get the new value.
You multiply this times this to get that.
Oh no. You would multiply the reciprocal.
Multiply by the reciprocal, yeah. Or just divide the original value by b. That's how you get the new value. So that's a formula that calculates the new period for you. It's the original value divided by b. So we already actually did some of these. What would be the period of sine 2x? The new period. Yeah. Pi, yeah. Remember 2, big number, causes the graph to actually get smaller. So the period is smaller. How about cosine 1/3 x? What would be the new period there? Yeah.
6 pi.
6 pi. 1/3 is going to cause the graph to stretch 3 times as much. So if the original period was 2 pi, 2 pi divided by 1/3 stretches it 3 times as much. How about c? What would be the period of sine pi x? Yep.
2.
2. It would be the original period divided by b. In this case, original period divided by pi. 2. How about this one, d? What would be the period of that one? About, yeah, Lens?
It would be like 2 pi over 3.
Yeah, it's always just 2 pi over the number in front of x. Stretching it by 2 and shifting it up 2, that does nothing. Doesn't affect the period. All right. So the last thing is making a table and doing the sketch. Which column does not change when we stretch left and right? Yeah.
Y column.
The y column. So the y column is going to stay exactly the same. Well, if the y column stays the same, then the x column is going to change. We're going to find the x's the exact same way we found the period. Just divide the values by b. Divide them all by b. And again, you might think, well, wait, are you multiplying by b? B's multiplied on the inside? Yes, but remember, it's the opposite. So if we divide by b, it'll automatically do what we need. All right, so let's try this one. Okay, so we just said y column stays the same. What are my y values for the graph of sine? Yeah?
0, 1, 0, -1, 0.
Yeah, 0, 1, 0, -1, 0. Now the original x's are 0, pi over 2, pi, 3 pi over 2, and 2 pi. According to step 2, we're going to take the original x's and divide them by b. Well, what's b in this case? Oh, all right.
2 or 1/2.
B is a half, yeah. So we have to divide all those values by a half. But instead of dividing by a half, what is it easier to do? Yeah.
Oh, just multiply it by 2.
Yeah, just multiply them by 2. Okay, when I have to divide by a fraction, then I think it's easier to multiply. So we're going to divide all the original x values by a half, which really means to double them. So 0, pi, 2 pi, 3 pi, 4 pi. And that's it. That will cause your graph to stretch out and be twice as long as the original. Okay, for our labels, I would just use 0, pi, 2 pi, 3 pi, 4 pi. So if you change your scale like I do, it's not really going to look stretched, but that's because you've changed the size of your axis spacing, which is fine. And that's your sketch. Okay, any question on that? Let's do, wow. Let's do that one. This will be our last one. Okay, multiplication inside. It's a horizontal stretch. Okay. What column stays the same? Yep, that's all.
Out of the y.
Yep, can you give me my y's for cosine?
1, 0, -1, 0, 1.
Perfect. Okay, original x's, 0, pi over 2, pi, 3 pi over 2, 2 pi. What am I supposed to do to all those x's? Raj?
Multiply by 3 over pi.
Right, we can either divide them all by b, but b is a fraction. So I'm going to think of it as multiplying them all by 3 over pi. So 3 over pi. Okay, and it might look like that's going to be kind of messy, but it's actually not. So the first one we get 0. What do we get for the next one? Yeah,
3 halves.
3 halves, yep, or 1.5. I'm just going to do that because I got to graph it. The next one, yep, 3. Okay, next one, yep,
9 halves.
which as a decimal would be? So like, you split 9 in half. 4.5, yeah. And then the last one, 6. And we get a nice pattern. It goes up 1.5 each time. Okay, so this is going to be the first one and the only one that doesn't have pi on the x-axis. So this time, I'm going to use 1s on both axes. So if I don't want to put labels, that's fine. So I'm going to graph 0, 1, 1.5, 0, 3, -1, 4.5, 0, 6, 1. And there's my sketch. Okay, we multiplied by pi divided by 3. That's just a little bit bigger than 1. So this caused it to compress just a little bit. Okay, not much, but just a little. Okay, so we normally don't go through transformations that slowly, but I thought it would just be good to go through it nice and slow. Okay, so that's each transformation. We didn't even do any multi-step like shifting and stretching at the same time. We're going to do that some other time. Okay, so the homework, it's not those questions. It's the worksheet that's in the video. So it's 8 questions in the Schoology. Okay, for each question, just make sure you make the table, and then there's a spot to make a sketch. I think there's a spot for maybe the original graph and the new graph. So just make sure you do that, and then we'll look at that spot.